example, I have, this is my solution. I have xn. Okay, then I get the tangent. This is a df dx at xn, the slope, right? Slope. So, so this is this distance is my okay. So this value is f at xn, right? F xn divided by the slope, okay, is equal to this. Okay, so this value equal to this value is partial the df, the f value. Sorry, f value divided by the slope. So this value subtract this value, so this will be my xn plus 1 location. Okay? So this is Newton-Raphson's iteration. I try initially xn. I got a value, this value, and I divide by the slope. I can get this distance. So I can get a new coordinate, xn plus 1. Okay? And after x plus 1, if I can get yellow. So first thing is I from here, I got a value. Then from here, I got a value fxn plus 1. And from this point, I got a slope. I get xn plus 2. From n plus 2, I got fxn plus 2. And from here, I get the slope. So after it will converge to the value with fxi, fk equal to 0. So the xk is a solution. So iterative, maybe 2 or 3 iterative, you can converge to the point. You can find the solution. Okay? So this is very quick. Instead of you draw this kind of a graphic method, you have to do a lot of, but maybe it's easier. Okay? You just let a graphic to plot it, and you can move your cursor to find location with function to be 0. And this is a way you try your best. Find a point close to it, and it will iterative converge. Okay? But after this, maybe you need to search in another route. Okay? So iterative. So this is if you can go to library to find a book, nonlinear equation solver. Okay? There's a method called Newton-Raphson method. Okay? In nonlinear finite element, we use a lot of this. Okay? You have to learn this. All right? So I just give you a basic idea. It's come from Taylor series. Okay? The increment is equal to the value divided by the slope. All right? So from this, you can solve this nonlinear equation and find the n0. Okay, maybe just the nonlinear, but maybe just one. Not maybe we do not have multiple root. maybe just one single root. For this problem, it's impossible to have two solutions, right? So only one n0 there. Okay? Cannot be multiple roots. So you can use the Newton-Raphson directly to get a solution for this n0. Okay. All right. So for this solution, what's the difference between this and the traditional beam theory? If you don't consider the actual force. So let's see. For a beam, it's roller. It's roller. That means we have a uniform loading. And this is my W. And the solution is, for this roller, you have a minus Q0 L4 over 12 EI. And Lx cubic minus half XLL fourths. Maybe 12, I forget, maybe you check, okay? Half X over L. Right? So this is a diffraction of this traditional beam theory. And compare with the solution of both side hinge, but on the same Q0, you have your diffraction, right? Diffraction. We compare the solution. So which one you think the diffraction will be more? Which one? If this is W from roller, well, W1 is a roller, okay? It's a roller. And this is a O, this W is hinge. Fixed, right? Fixed. Okay. So which diffraction will be smaller? Which one? This idea like a tendon. So this should be stronger. Like hanging bed, right? You have a force to pulling it. So this one should be smaller than. Oh. Okay? So we have a plot. And this non-dimension curve. And this is diffraction at the middle. Okay? Diffraction at the middle. So this is a middle. And this axis is the loading, Q0 L4 over EI. Just like this. Okay? The value of the loading. And for different Q0, you have a different W. So the relationship like this. This is a W roller. And this will be with fixed hinge. So that means for the same loading, this is a W R. This is W fixed at half L. So for the same loading, the roller will provide more diffraction. Okay. So from design point of view, I think it's better, right? Because this is not too conservative. You say, I'll give loading, well, I'll give a bigger differential. This is more conservative. Okay. Much safe, right? So you say, yeah, you overestimate your diffraction, but the real diffraction is smaller. Yeah. Okay, so this is yeah, we spent 2 hours to to show the theory, okay. But it contains a lot of things. So you see, we still have another example for beam hinge, but the loading is this loading. Okay, so my Qx is not a constant. The Qx is x over L Q0. Okay. Okay, it's linear, and we also have a tension force. Okay, so you have to try to get a particular solution. Use the undetermined coefficient method, okay, as notes. Okay, so you just look at by yourself, right? So this is for example 2. Okay, you still need to find the Q and N0. Okay, N0. Yeah. Okay. Yeah. Do you want homework? No? No? Okay. Okay. Okay, Thursday we are going to talking about not the tension. The actual force is compression. That become a buckling problem. Okay. For this kind of a beam with tension, we call this the tie beam. And Thursday we'll have a beam with compression loading, and this will become we call the beam column. Okay, because the column is for actual compression. So this kind of a beam we call the beam column. Okay, if you put vertically, there will be a column. Okay, we call beam column, and this tension we call tie beam. Tie beam. Okay, 2 different names. All right, so that's for today. So today you learn a beam with actual tension. Okay, yeah. So, Mingyao, you have used your program, shell, to solve this tension, but also can for compression. Okay, it's a narrow width plate shell. Okay, just shell element to do this kind of. You can try. Okay, yeah. See the, yeah. Do some benchmark testing about your program is correct or not. Okay, 好吗？试试看。All right, that's for today. Yeah. Okay.